model of some kind, and that can be a diagram, that can be some words, that can be all kinds of different ways you can express your model. But until it's explicit, it's not going to change. When it gets confronted, because we live, it's natural that we live with contradictions in our heads. I mean, I drive down the highway, and I drive as if everybody else is going to obey the rules, and at the same time, I drive as if sometimes some of them aren't. Right? So that's a contradiction, and we can't resolve it because the real world is like that. Science gives us the luxury of taking the time to resolve contradictions. But you can only do it if you know, if you can see the contradiction and you're facing it, and then you have to work to resolve it. And so resolving contradictions is something students have to do in order to change their mental models. And the first step in that is making their mental model explicit. And then developing and refining it, working to make it work to explain the phenomenon they're trying to explain. They have to do that in groups, and they have to argue and figure out what they observed and what they saw and what happened and what didn't happen, and whether or not it matches what their model predicts would happen. And they have to incorporate, as they work, more and more science knowledge into the models that they build. So, and then use those models to support detailed explanations that explain the phenomenon. So let me go through these practices in a little bit more detail. Again, those of you who have been working with NGSS have seen the lists, and here they go. This is the first place the word engineering approved up here, so I'm going to stop for a moment and talk about it. Why do we put engineering in science? It's not science, it's different. However, there's two very core reasons. One is that for students doing the engineering projects, doing design projects, applying their science knowledge is as important as learning their science knowledge. Again, because you get to be able to apply knowledge by practicing applying knowledge. Secondly, engineering and technology are endemic in our world today. And before, if we go back like 5 years before STEM started to become a word that everybody was talking about, kids could go through 12 years of school and perhaps never hear the word engineering, and never know what engineers do, and never meet problems where they had to apply a design cycle and really think like engineers. So just as it's important to learn to think like scientists, it's also important to learn to think like designers and engineers. And it fits so easily. Look at this. We have 8 practices, but only number 1 and number 6, it says 2, but it means 1, are different for engineering than they are for science. Where you start, in science it's asking a question. In engineering it's defining the problem for which you want to design a solution. And at the end, in science it's developing the explanation, and in engineering it's developing the design. But all the rest of the practices, those are things that engineers do and scientists do. They do them for different purposes and in slightly different ways, but they're so similar that putting science and engineering together in the curriculum makes a lot more sense than just adding engineering as one more separate thing that you have to learn. So we decided, the committee that wrote the framework decided engineering really needed to be part of science, starting in the early grades and working all the way up. And the second thing is, when you talk about inquiry science, yes, students were asking questions and carrying out investigations. But in all too many classrooms, the things that are in red were not what they were doing. There was no interpreting data, no engaging in argument from evidence, no evaluating information and communicating it. So all of these practices are what I did as a scientist and what must be done to learn science. And it's not just 1 or 2 of them. And by the way, they're not that separate. It's very hard to develop a scientific explanation without engaging in argument from evidence or interpreting some data. Right? You've got to put these practices together so they work in the classroom as they work in science. But having the list is just the beginning of the process to having kids doing all these things in the classroom. And for teachers who are just starting down this path, just picking one of them, I'm going to have my students do more modeling, or I'm going to have my students do more arguing from evidence, begins to move you in the direction of the next generation science standards and away from the old California standards, which although they had science and investigation skills on the side, had an awful lot of just learn these facts and don't ask why. So, practices are used to make sense of phenomena. Models are used to support explanations. Argument from evidence is used to refine your model and develop your explanation. Of course, in doing that, you have to apply science concepts. Data by itself is not evidence. Data has to be interpreted to be used as evidence for anything. It has to be analyzed and organized and thought about in different ways before you can ask, does it or does not match what this model predicted. And explanations, of course, always lead to new questions. That's one of the things about the nature of science that I love, right? The more we learn, the more we have new questions we can ask. Questions we couldn't even ask before because we didn't know enough to ask them. So that's how science works, and it's how science learning works, too. Okay, so students must do these things, and I say it over and again because I think it's incredibly important that the process of doing science is part of the process of learning science. Not that we expect students to rediscover what scientists have discovered by hundreds of years of work, but because the conceptual change process requires integrating the knowledge by trying to work with it. And so all of these practices are critical to learning. And then also reflecting on the practices, reflecting on the nature of science and the difference between science and engineering to help understand metacognitively what is science and what is engineering. Now, I keep stressing this, explanation are not the theories of science. They're explaining a particular phenomenon. All right, I'll give you an example. Talk to the person next to you. Explain to me, why is it easier, or explain to your neighbor, why is it easier to ride a bicycle uphill in low gear than in high gear? Just talk for a few minutes.
That's where it's more resistance, I don't know as much
And she likes the virtual model.
That's what it is. So you can use the energy from the environment more efficiently. Because if you were a rocket, you couldn't roll it all around too tight.
You can also actually, one of the ways you can answer this question is go online and find the answer. Which is fine. That's a perfectly allowed, that's a practice, right? Obtaining, evaluating, and communicating evidence, that's a practice. Waving your hands was the process of beginning to develop a model, right? You were engaging in about 5 of the practices in those 2 minutes of conversation. Just have to think and break down your conversation and you were trying to develop an explanation. You were trying to take the evidence you know about bicycles and how they work and apply it to answering the question. You were active and engaged and interested because you had a real phenomenon to think about, and it's worth working to understand that phenomenon. And if you're a high school physics teacher, you would explain it one way, and if you're an elementary teacher, you'd explain the same phenomenon with different language in a different way. But all of you can focus on the phenomenon and begin to move towards an understanding of it. That is the essence of the way science should be learned. And it works, folks, it works. So try it in your classrooms. As I said before, knowledge that is used, knowledge that is applied, is more likely to be remembered, is more likely to be applied when you come to a new problem selection situation, and it's more likely to be connected in your brain with other knowledge and skills. So the whole notion of building a coherent structure of knowledge in your brain, the three-dimensional structure of knowledge, requires you to use the knowledge as you learn it. And this is the message. So, developing models. It's not just learning about the models that scientists have made. It's developing your own and then refining it and incorporating your knowledge as you learn about it, about what scientists have understood about this phenomenon. Explaining specific phenomenon, incorporating both visible and invisible ideas. So how many of you, when you were talking about the bicycle, used the term force? The physics teachers in the room. How many of you used the term energy? A few more. A lot of you just were thinking about distance and how you didn't have to push as hard, right? There's lots of, the physics concept, if you want to know it, is force times distance equals work done. And if you apply a small force over a large distance, you can get the same result as a big force over a shorter distance. And it's much easier because of the strength of your body to do the first than to do the second. So the idea is there. It's a science idea. Now that you've been talking about the bicycle, you're much more likely to remember what I just said about that idea than if I just taught it to you when you didn't have a context for thinking about it. And so the place for the teaching slips in when the phenomenon grips enough that there's room to learn something new in order to be able to refine and develop your explanation. That's the way science teaching can work. Yes?
Have you developed a teacher's edition?
Not yet.
Are you working on that?
There's a lot of people working on that, actually.
Is that what you would recommend?
None of them exist yet.
Okay.
Right? You can go online, you can find, for example, places where people have been. How many of you are in one of the early implemented districts? So a few people who have been working on that who are in this room. You can see in many of the displays over here, people have been working on that. And there's online resources and there's some online professional development around resources. So I'm not going to point you to any one at this moment. And I would, when you're talking about district adoptions, I would advise you to wait because there's more coming. But developing what you need to do what you can do your next steps based on the curriculum resources you have, refined and modified to engage students more in the practices, to think more about the cross-cutting concepts, and you'll get there. But these are the important features of models.